All right. Good afternoon, everyone. It is 3:30 p.m., so it is time for biochemistry. Um, the first thing that I want to go ahead and bring up is that the content that we cover today in class will not be on your first exam. So your first exam, basically everything from there, all stopped last, what was that, Wednesday. So I will talk about some things, and I don't want to sound like I'm immediately being hypocritical, but I'm just going to bring back up some things that we talked about last time. I just want to kind of clear up any sort of confusion, and that will be on this exam. But any new things today will not be on the exam on Thursday. The second thing that I want to bring up is your practice exam. I'm going to be posting that later today. I apologize for my delay. My wife's grandmother passed away, and it's been, kind of chaotic and hectic trying to figure out, like, what are we going to do? Not what are we going to do, like desperation, but just like logistics of it. Now, with that said, I will get that done. And then tomorrow, thank you very much. I appreciate that. Tomorrow, I'm going to have a review session. It's going to be in the afternoon. I'm going to have it for an hour, roughly. And then I'm just going to work through the practice exam. I'm going to record it. And so if one person shows up, great. If nobody shows up, not great necessarily, but that's fine. I'm going to record it. I'll post it on our Canvas page so you guys will have access to that. So I will do that. I think it's probably going to be about 1 p.m. I'm doing the same thing for one of my other classes. So I'm going to do both of those. And I'm just going to work through the questions and give you a sense of like, hey, this question is a style of question that I like. Can you repeat the day for that? So tomorrow is the day of the review session at around 1 p.m. I'll send an announcement, and I'm going to put that on my JWG. Those are my initials. Joel William Gray. Announcement 4375 review. So I'll post the announcement around the same time that I post the link for the practice exam. And like I said, I'm just going to work through questions and say, hey, this is a good, or, I gave you this as a practice question for a reason. Here's some ways that you could kind of make your own sorts of questions, how we could look at it from a slightly different angle. Your exam is on Wednesday, and I'll send you more details about that a little bit later today, just so then you have like a hard copy of things. One thing that I am going to clarify is your exam is going to be just like your quizzes that have been administered through Proctorio. So you will have Proctorio, but one thing that I'm pivoting on is I am going to be available on Zoom. So if you encounter any issues during the testing period, by all means, join the Zoom on a different device and say, hey, I'm having an issue. I don't know what's going on. I haven't been able to log in, whatever it is. I'll do my best to help you out with that. The next thing is if you're taking your exam in the testing center, then I believe that I've communicated with the testing center and the folks who are doing that to arrange the time and everything like that, and kind of the parameters of your exam. But if anything comes up during your exam or before your exam, please don't hesitate to contact me. I will have office hours on Wednesday. So we're taking the test with Proctorio instead of the whole setup. Yep, just Proctorio. Just Proctorio. And so, yeah, if anything comes up, let me know. I'll send out some more information about the exam and what to anticipate and everything like that. And what you should expect to see on the exam from me. For instance, amino acid pKa values, I'll give you those. In addition to that, I'll give you a periodic table because heck, as maybe like a security blanket or like I'm just comfortable with seeing a periodic table. Is it during our scheduled class time? Yes, it is. Thank you for asking that. Your exam will be administered during your regular class time. So starting at 3:30, and ending at about 4:50. I do build in a little bit of a buffer there, so maybe I started at like 3:15. So if you're someone who, okay, cool, I can get started at 3:15 by all means. There will be 60 minutes for the exam, and it's anywhere between 30 and 35 um, multiple choice questions. So there's always going to be, whenever I'm writing an exam, I always look to a certain number of questions as being kind of the like slam dunks. Those are going to be your gimmies. And it's not like, oh, 80% are going to be gimmies. But there's some that are just like, are you familiar with what's going on? Okay, sorry for your loss. Also, um, okay. So are we allowed a piece of empty scrap paper? Yes. You can also use a one. And Emily, yes, no weird camera setup. Yes, no weird camera setup, just a regular Proctorio. Um, One note card you can write on the front and the back. Um, can we ask for extra time on the exam, or do we have to go to the testing center? No, I can accommodate additional time. So anyone with accommodations through ODS, I will provide that time and make sure that, won't the exam won't randomly shut down on you. I'm kind of taking that into account. Um, will Proctorio flag us for head movement if we look at our cheat sheet? It will, but the good thing is, and what you guys should keep in mind, is Proctorio doesn't decide your grade for you. I'll look at the exam and I'll scrub through the video. It gives me a little score and it says like you get, there's a 94% chance that this person was doing something suspicious. And then I'll scrub through the video and there will be certain times. And Proctorio does what I've seen is it kind of works on both ends. It works on like odd confusing movements, but then also it works on, or sorry, it picks up on like no movement. So if you sit like this for the entire exam period, then it's going to be like, well, that's weird. And it's going to let you know, or it's going to let me know. Sorry, just a second. Um, so, okay, is this good for colors? The plan is for this to work for all of your exams. So anyway, my point was that Proctorio will give like me a notification for lots of movement or minimal movement. And I just sort of scrubbed through the video and I'm like, that is weird. What's going on there? Um, then will we show our note code before the exam? I remember you had mentioned it before. Yes. So basically at the very beginning, I'll get a prompt, or I'll give you guys a prompt like if you use the note card, hold it up. Like a head tilt down won't get flagged, or should we show the note card at the beginning of the class or at the beginning of the exam? I'm just going to say like hold up your, or sorry, the first thing, the first question, basically, it's not a graded question, will be hold up your note card. Um, okay, okay, I'm sorry. And and the thing is, when you hold the note card up, Proctorio is going to be like, "What's going on there? Can we use an iPad to take the exam?" I don't think that's going to work. From my understanding, people don't have success using a a tablet of any sort, whether it's an iPad or a Fire book or Chrome. Um, so Proctorio doesn't really work with those. I wouldn't worry about this. He knows we'll do it. Yeah, he does. Okay. Um, all right, everyone. Well, I'm going to go ahead and so we can take the exam on a computer and then join this Zoom in the event that you need to join the Zoom. So if you have questions, but you do not have to. Okay. Um, now, Proctorio prefers, yes, Proctorio does prefer Chrome. Um, will be, yes, Proctorio will be the lockdown browser. Um, and I have a class that ends at 3:20. This is a private message, so I will be a few minutes late. Just want to let you know in advance. Okay, understood. So in the event that you've had any issues with taking the quizzes, I need you to let me know just so we can kind of sort that out. But from what I've gathered, it seems like that hasn't been a consistent or recurring issue. Um, in the event that you hear any background noise, that's two of my kids. But for the time being, I am going to go ahead and jump into talking about protein purification. I'm going to kind of do a quick summary over what we were talking about last time. So if you remember last time, one of the things that we were talking about was protein purification, and we were talking about column chromatography. Now, we talked about two different types of column chromatography. We talked about size exclusion chromatography, and we talked about ion exchange chromatography. Now, one of the things that I would recommend with respect to these is to like don't get distracted or overwhelmed by like distinguishing between them, but I would recommend thinking about what makes them all similar to one another. I'm going to show you this right here. This is ion exchange chromatography, and then I'm going to jump over to size exclusion, also known as gel filtration chromatography. Now, what I want you to recognize about these two different techniques is, first of all, the column. Okay, I just pointed an arrow towards my size exclusion or gel filtration chromatography column, and then this column. I mean, they look pretty similar to one another. And for all intents and purposes, they are. They do look very similar when when you get the column in the mail and you look at it, oh, that looks very similar to this. Now, if you get down to the microscopic level, you're going to see some things that also look a little bit similar, and that is the beads that make up the resin. So this resin is also known as, and if you think about chromatography, there's, oh, sorry about that. Boom, enable. There's two different types of, or two different major parts of chromatography. One that I remember is your mobile phase, and the other is your stationary phase. Now, this right here, that's going to be your mobile phase. Your mobile phase is the solution that your pure, your impure, or your not yet purified protein is in. Your protein is in the mobile phase. Now, your stationary phase is made up of lots of insoluble, insol beads. Now, these beads are all going to be very similar to one another, whether you're talking about ion exchange or IEX chromatography, or gel filtration or size exclusion chromatography, GF or gel filtration. You're still dealing with a stationary phase that has these little beads. Now, the difference between these two types is, well, if you're talking about ion exchange chromatography, the beads have a charge. So what that means is we've got some sort of functional group added to them with a charge. So let's say that we put a carboxyl group on. Carboxylate ion, okay, that's going to be a negative charge permanently affixed to that bead. Okay, could everyone give me a 5 in the chat if, okay, cool, I've got that. It's permanently affixed to the bead. Okay, now thinking about that, this permanent kind of fixture on this bead is negatively charged. It's going to be really good at capturing positively charged proteins or proteins with positive charges on. So, something like a protein with a bunch of histidines or maybe some lysines. Yeah, lysines and arginines are both going to be really good candidates. So if you have a protein that on its surface has a bunch of lysines or arginines, then you've got you could comfortably say that it's a cationic protein. And you want to capture that. And so you're going to use a resin that has negatively charged species permanently affixed to it, because then they'll kind of hold on to that protein whenever it flows past. Okay, this is kind of a review of what we talked about last time. So if the functional group on your resin is negatively charged, that would be a great example of a cation exchange column. And maybe you want to narrow it down and say, well, a cation exchange resin. It's another way to describe it. Okay, so in the event that instead of doing ion exchange chromatography, we're talking about doing gel filtration chromatography. We've got these same insoluble sugar beads. The difference is that these beads, these spheres, it's almost like we got a bunch of, I don't know, let's say earthworms. And we're like, hey, earthworms, dig some little holes through these, burrow some little holes through these beads. So you've got these beads that kind of look like a wiffle ball of sorts. And these proteins or proteins of different sizes will either enter those pores, enter those holes in those beads, or they won't. Okay. Now, in the event that a protein does not enter one of those pores or one of those holes in those beads, that protein is going to migrate through that column very quickly. We've got that represented by this large green protein. So our mobile phase here had proteins that were, I'm going to go with P for purple, G for green, and Y for yellow. The green beads, they basically saw that opening and were like, nope, not going to happen. They noped their way right out of that. And so they flowed through the column very quickly. They migrated through the column fastest. So the larger proteins elute first. So largest, pro, elute first. Now, the second piece of information from this is in this case, we've got a visual here. We've got our yellow, moderately sized proteins. Well, those, I always kind of think that they almost like they hit the top of that and they're like, yeah, I could. No, I can't fit. I'm not going to. So they got a little bit delayed in this process. And it's almost like, I buy a new pair of pants and I'm like, I've slimmed down, Joel. It's time for some. Nope, not going to work. Not this time. Not this time. So there was a little bit of a delay. Tried pulling the pants on. Nope, not going to work. So back to sweatpants. Now, with that said, these yellow proteins, they have a little bit of a delay. So those are going to be the ones that elute second. So I'll say our mid-sized proteins. The Honda Accord of proteins elute second. Second. And then third, last but not least, is our smallest proteins. Those smallest proteins, they enter these pores. And remember last time I was talking about how they basically migrate around, they're making contact with the entirety of the interior surface of that pore. So they're going to begin migrating through and they just revolve around over and over and over again. Now, that is going to be our smallest proteins. Proteins elute last. Now, just one moment. I'm sorry, I have to mute. Okay, so our smallest proteins elute last. So you can kind of operate under the idea of an understanding of gel filtration that the largest proteins elute first. The second proteins, or the second largest class or group of proteins elute second, and then your smallest proteins are going to elute last. So the smallest proteins stay in that column for a very long time. So the difference between gel filtration and ion exchange chromatography is really just how these beads are modified. For gel filtration, we drilled holes through the beads. For ion exchange chromatography, we did some sort of covalent modification to permanently affix, and I always try to use that phrase a lot, permanently affix a charged species onto them. Okay, so could you give me on a scale of 1 to 5, 1 being, man, I've got the difference between these two, and 5 being, what's an exchange? Okay, so I'm seeing, okay. I'm happy to see some of those good lower numbers there. All right. Now, those are two major types of chromatography. I want you to remember that these two types of chromatography will be on your exam on Wednesday. Now, the difference between what's the purpose of the pores in the beads for the smaller proteins? Could you use some sort of funnel system to have smaller beads go down first? Well, okay, so that's a great question. The purpose is when you're separating proteins, um, and I'll use numbers. I'll say that we've got, okay, so when we talk about the size of proteins, proteins vary based on their molecular weight, and their molecular weight is directly related to number of amino acids. Okay. Now, the unit that we use for describing an amino acid is one amino acid, one AA, whether that's histidine, lysine, arginine, leucine, whatever. We have kind of an average number. Each amino acid is approximately 107 Daltons. Now, you could also look at this and say it's approximately 0.107 kilodaltons. A Dalton is just a unit of measurement. I think that a Dalton is equivalent to 1 gram per mole. And whenever we talk about these, that measurement scale, think about if you had a protein that was, I'll go with my largest protein here. Let's say that this was 765 amino acids. I think I'm having a bit of trouble understanding this because I'm thinking of them as ion channels. Wouldn't it make sense for the smaller proteins to more freely squeeze by? I like your thinking, and I'm going to come back to that in just a second. Now, the next would be, let's say that we've got one that's 350 amino acids. And then the last one, let's say that it's 125 amino acids. Okay. So this, let's say that the opening in this bead can accommodate a up to, so I'm going to draw a circle here, something up to 200 amino acids. That would be the same as approximately 20 kilodaltons. Okay. Now, that is going to be a good size for separating this smallest protein from these two larger proteins, because these two larger proteins, they'll see that opening and be like, not going to fit. And so I'm going to move straight through. Now, if we were to separate, okay, and so the question that I got that initially triggered this was, what's the purpose of the pores in the beads for the smaller proteins? Could you not use some sort of funnel system to have the smaller beads go down first? Well, it's not really a matter of, okay. So when we load these three proteins in as a part of the mobile phase onto this column, at this point in time, as far as we're concerned, these are microscopic. We can't even begin to visualize them with maybe even some of the strongest microscopes. So it's almost like these are, you could almost think about them as like, oh, they're really small ants versus small ants. They're both small, they're both minuscule to us. So, in terms of, oh, could I just sort of separate out based on this physical property and the size of them? It's not quite that simple. That's what we're doing with this column. That's why we would do this. So, we're going to load all three of these onto this column in this as a part of this mixture at the same time. And whenever we do, these pores are going to be our mechanism to select and separate these proteins. So this largest protein right here, it will try to enter that port and it simply can't. So it's going to move straight past. So those are going to elute first. That's what we see in these tubes number 3 and 4. Our mid-sized proteins, well, they'll try and they will maybe have a little bit more success, but they're still going to get delayed migrating through the column. The third protein, and I'm sorry, usually I have like a soda can or something, something cylindrical. Well, I only have vacuum attachment. That doesn't really help. So, um, dang it. Yeah, usually it's weird. It's marginally clean in here. Um, so, well, yeah, I'll just imagine that this medicine bottle right here. When you put that 125 amino acid protein in here into this tube, it's not a matter of like, let's say that there's a large protein, it's going to try to enter, it can't, so it's going to move past. Okay. A slightly smaller protein is going to get stuck and it's going to be like, oh, I can't make it through. Okay, now I'll move on. A very small protein is going to be like, oh, I can enter there. But it's not going to be like, choo, slide straight through. Instead, this is what I was talking about last Wednesday, where it makes contact with the entire interior of this, basically this tube, this pore through that tube or through that bead. So it kind of, it's almost like it's riding the entire circle of that. It's sliding down, making contact with the entire interior of that pore. So for the person who asked, I'm thinking of ion channels, wouldn't make sense for the smaller proteins to more freely squeeze by. It's, I think that the stationary phase is so well packed and the concentration or the number of these beads is so high that it's not a matter of slipping straight through. Instead, it has to migrate through. It will be kind of captured within those pores. Okay. 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 I got response from the first question. I'm not sure about the second one. So potentially a dumb question, but does it ever get stuck like a kidney stone when it's too big or is in my receptors? Okay. I got an okay. Okay. That's a great question. So let me just tell you kind of from the benchtop. When you're doing like, if you get, let's say you harvest a bunch of E. coli, that means you grow the E. coli for 16 hours or 8 hours or something like that. Could anyone tell me something that E. coli has that plants also have? And yeast also have it as well. Add it to the chat. Smelliness, I like it. Thank you very much. They do. They have cells, yeah. What's around those cells, though? I'll give you a hint. There's one back here. Cell walls. Absolutely. And cell walls are these dense networks of sugars. They have sugars and fats and a bunch of junk there. And it's just like a cell wall of a plant. Now, with that in mind, cell walls can be very extensive. And so when you're trying to purify a protein, let's say that you got here, I'm going to draw my beaker with my E. coli. There's my E. coli cells. I'm really just trying to illustrate that it's like a murky solution. I've got a bunch of E. coli cells going. And if I were to take this and load it directly on here, to the question of would it ever get clogged? Absolutely. So when you're purifying a protein, I can't go directly from, hey, I've grown some E. coli, let's throw them onto this column. Could you give me a 7 if that makes sense to you? Okay, great. What I'm going to do is there's actually a lot of preparation work. There's a lot of prep work. The first thing that I'm going to do is something that you guys have done in Gen Chem 2. Centrifuge. I'm going to centrifuge it. I'm going to spin these E. coli cells down, and you know what? I'm going to get a test tube, and I'm going to have a solution, and then there's going to be what's known as a cell pellet. That cell pellet has a bunch of junk. It's got a bunch of cell walls, it's got a bunch of insoluble proteins, but it's got all of my cells. And within all of my cells are my proteins. This solution up here, I don't care about that. I don't want that. That solution has nothing that I need. What I need to do is I need to figure out a way to basically take these cells and blow them up and rupture them. And that's a very important part of protein purification. So in that process, I guess my point to the question of can it ever get clogged? Well, if all of these prep steps are not done well enough, then absolutely. And whenever that happens, these columns right here, these gel filtration columns, which can be very expensive, they'll stop working. And you won't be able to separate proteins of any size. Okay, so what I want you guys to take away from this is I want you to understand the principle on which gel filtration separates things. I want you to understand, I want you to know the number of Daltons that one amino acid is, roughly, and then I want you to understand relative sizes of proteins. 700 amino acids, 300 amino acids, being able to evaluate like this is the largest, this is the smallest, and so on. Now, this is kind of my review from last week's stuff. Now, the last thing that I say about this last week's stuff before I put the starter questions up is when you separate based on gel filtration compared to ion exchange. With ion exchange chromatography, you have charges that attract. Opposite charges attract one another. And you know what? That opposite charge is going to stay there until you do something like you try to release those proteins by changing the pH of the solution flowing through there. Anna asks, so those numbers are arbitrary and just for example, like to be able to tell that 700 is larger than 125, so it'll dilute first, or are those? No, I like that, understanding that a 700 amino acid long protein is bigger than a 500 amino acid long protein. Thank you for asking that question. Okay, so you can elute a protein from an ion exchange chromatography column by adjusting the pH because it's charge-charge interactions that drive a protein to get stuck. Gel filtration chromatography, man, oh man. This is something that doctors have a lot of, and my wife has a lot of. And that's how you separate based on gel filtration, or the principle of gel filtration. Patience. You just got to wait. You just got to let it sit and watch and wait and go, okay, I've collected. Here, can everyone give me a Y or an N if they understand that these are the fractions, the roughly 1 milliliter fractions that come off the column? When you're doing gel filtration chromatography, you might have 275 fractions. And if you're using this pump right here and you're flowing this solution through at, maybe 0.1 milliliter a minute, okay, 0.1 mil per minute, you have and this is not an important number for you to remember. I'm just trying to emphasize the point that you just wait for this to take place. You'll have 0.1 mil per minute flowing over this column. So that means it's going to take 10 minutes for 1 mil to flow through. And you're flowing 275 mils total. 275 times 10. And I'm doing this math to really emphasize this takes a long time. 2,750 minutes. I don't know. That's like 40 something hours. 50. No, not 50. Yeah, that'd be about 40 hours. So I'm using a really crooked number there to say that you just have to wait. Gel filtration, slowly but surely, every protein will elute through that column. Okay, now I want to give you the opener questions for today. I'm launching those. I'm going to give you a second on these, and then I'm going to go ahead and proceed. Take a drink of my drink.
Who made this one team? No one.
Okay. So I'm gonna leave those questions up for at least 5 minutes. Make sure that you answer them. Now, a third major type of chromatography or column chromatography is separation based on attraction. This is known as affinity chromatography. Now, this is a type of chromatography where, again, you've got these beads, but you know something about your protein. So let's say that you were trying to purify a protein pro that binds, let's say, the sugar glucose. What you would do is you would take this bead. I'm going to put an X over the bead, and then you would put a glucose molecule on it. And when you put that glucose molecule on that, there's one property of, or that it's going to be very good for. Every protein that binds glucose is going to bind that glucose on that immobilized bead. Well, let's say that we have proteins A and B. Protein A is mostly negatively charged residues. And protein B is mostly positively charged residues. Ooh. Protein A is 625 amino acids. Protein B is 315 amino acids. Did we only cover secondary structure as far as protein folding? Yes. Don't worry about it. Okay, so these are properties of proteins A and B, and proteins A and B both bind glucose. Okay. So protein A is mostly negatively charged residues. Protein B is mostly positive. Protein A is 625 amino acids, and protein B is 315 amino acids. And protein B and A both bind glucose. And then I'm going to throw a third protein out here. Protein C is mostly positive residues. It's 455 amino acids. And what does it bind? It binds, let's say that it binds
No, it's not gonna be.
alanine.
It's not the magic number.
Okay. Now, if you had a mobile phase, I'm going to say you got protein A, B, and C all mixed up. And then you had this bead right here that had a bunch of glucose permanently affixed. So this right here, could everyone give me a Y if they understand that orangish red sphere represents a glucose molecule? Just as an example, I want to stress that this is just as an example. Um, well, we've got proteins A, B, and C all mixed up. Then let's look at column, or we loaded this on our column. And if you look at test tubes 3 and 4, there's proteins there. Is that going to be proteins A, B, or C? Or is it a combination of A and B? Or is it a combination of A and C? Add to the chat, what letter protein do you think is in fractions 3 and 4 there?
I never wanted to put one.
Keeping in mind, we've got these beads right here that has a bunch of glucose immobilized on it. I got to vote for C, and then I got to vote for A and B. Well, keep in mind, A and B will both, absolutely. So, mixture of A, B, and C. This stationary phase has a bunch of beads with glucose molecules on it. Proteins A and B will bind glucose. They will bind glucose and just stick to it. So if there is glucose on these insoluble sugar beads right there, proteins A and B are like, ooh, I see glucose, and they'll get stuck and they'll stay there. Protein C, by comparison, what do we know about protein C? It binds alanine. Does protein C bind glucose? Nope. So protein C says, I don't care. I go straight through the column. So these fractions 3 and 4, that's protein C. And I'm sorry if my awkwardly constructed question was a little bit confusing there. But what we've got here is proteins A and B. They both have this function where they are both able to bind glucose. So I want you to give me or to think about it this way. If we used affinity chromatography, we are exploiting the fact that a protein has an affinity for a substance. It has an affinity for glucose, as an example. So we make these beads that have glucose permanently affixed to them. If we had a mixture of A, B, and C, this column would be great for separating proteins A and B from C. But would it be useful? Give me a Y or an N. Would it be at all useful for separating proteins A and B from one another? Not at all. You're absolutely right. Oh, Anna, you asked the question that I always want somebody to ask. So thank you so much. Is it always glucose, or can it be anything that can be seen? Yeah, absolutely. In this case, I'm just using glucose as an example. But when it comes to affinity chromatography, basically you get the bead and you say, you know what? I want to find a protein that is capable of binding to, let's just go with, and we could use a nitrogenous base. We could also make the molecule, and, if you think about a nitrogenous base, you're talking about, what would that be? Nine atoms, a little bit more than that. It could also be a DNA sequence. Maybe that's 10 base pairs long. BP long. Okay. So the size of the substance that you affix to these beads, that's at your own discretion. But let me ask you this question. If you are trying to, let's say that you extracted, let's say your source material was like human blood or something like that. And you got all the soluble proteins, or maybe like gut bacteria. You got all the soluble proteins from all the gut bacteria. And you said, ooh, I want to find all the proteins that bind glucose. Do you think you're talking about one protein? Do you think you're talking about quite a few proteins? You probably are. So it's probably going to be a pretty jumbled mess. It's almost like it's going to be kind of challenging. And so that's why affinity chromatography, I don't want to, badmouth it as a technique, but what I do want you to think is, okay, this is a potentially powerful technique, but it has limitations. In this case, it was great for separating proteins A and B from C. But when it comes to separating A and B, could anyone give me a separation technique that would be great for separating proteins A and B from one another? Perfect. Gel filtration. Gel filtration would work like a champ. So would ion exchange chromatography. Now, I want you to now take a step back, and this is the sort of question that I want you guys to be able to solve. If you had that original mixture of proteins A, B, and C, could everyone give me a Y in the chat if yes, I'm there? I've got it. Okay, you've got A, B, and C. You look at the properties of A, B, and C. Let's say that you wanted to get rid of proteins B and C. Could you do that? The answer is yes. But could anyone tell me in the chat what type of, I guess, what type of separation would you use for that? This is a tricky one because I know, okay, Ion, can you peel the next layer of the onion back? More specifically, my question is basically, is it cation or is it anion exchange? If I wanted to get rid of B and C, okay. Oh man. Okay. This is kind of tricky because I think that you guys, what I was going to say was, hey, I'm going to give a bonus point for participation. Actually, I'm going to give a bonus point on the exam. I'm going to write that down. Exam VP, bonus point, as opposed to base pair. I'm seeing both anion and cation as answers. And you know what? You're actually both right. Sammy, I don't know if you would like to change your name to Slammy for the purposes of the slam dunk that you just delivered for class, fantastic. I support that. So Sammy's absolutely right. You could do it both ways. Now, here's why. If we've got one negatively charged protein in a mixture of, well, two positively charged proteins and one negatively charged protein. Okay. If we use the cation exchange chromatography column, that means our beads are negatively charged. So give me a 5 in the chat if, okay, cool, I'm with you. I follow. We've got our beads that are negatively charged. So this is a cation exchange chromatography column. Our protein A, what it is going to do is it's going to look at the beads and it's going to say, I don't care. The beads are the exact same charge as me. I have no attraction to that. Meanwhile, proteins B and C, they're going to be like my kids whenever I say, hey, I got to stop at a gas station. They're like, candy? And I say, no, gasoline. So those proteins, B and C, they're going to get stuck to the column. But protein A goes straight through. We were separating A, B, C, not B and C. We were trying to isolate A from that mixture. And so the protein that does not adhere to the column flows straight through. And that happens to be what we're looking for. So one of the things that's super important about chromatography, column chromatography, is that there's a tendency, especially when you talk about affinity chromatography, there's a strong tendency to be like, oh, that's the best. That's the best type of chromatography. When in reality, none of them are best. They are great for specific applications, but there's not one that's like, there's not one Lord of the Rings to rule them all. There is kind of a tendency for people to do kind of broad brush chromatographies, like they'll do ion exchange chromatography, because effectively you'd say, oh, well, I want to get rid of all the negatively charged things. Okay, cool, I've done that. So if you want to catch a negative molecule, you need a cation exchange column. But if you need to separate a negative and positive, you could either use both ways or they'll both be separated. Okay. If you want to catch a negative, okay, in cation exchange chromatography, think about cation exchange. The beads are negative. Anion exchange. Beads are positive. Now, Anna, I'm sorry for kind of taking a step back on your question and not answering it directly. The most important thing to me is that you understand what is the composition of the bead. Because when you understand the composition of the bead, then you can be a little bit more tactical and surgical with your, well, what am I trying to do? Because, you know, if we go back here and we say, oh, well, A, B, and C, we've got those proteins. The folks who said, oh, well, I used an anion exchange chromatography column, that would also work. The reason is because in that case, so anion exchange, I'm going to draw my column. Here's a bead, here's another bead, positive, positive for an anion exchange. The beads are positive. So protein A is going to hang out with these and be like, sweet, I can dig it. I like this. This is good. What are B and C going to do? They're going to say, nope, straight through, not stopping. It's not, I don't like to stop here. Okay. So when you so that's why this detail right here is what I would recommend kind of falling back on, because then you can use that for what am I trying to do? Okay. Now, um, so affinity chromatography will not be on your first exam. Um, but think about this as okay, cool. This is another layer of like technical separation that I'm learning about. So the level or the style or the complexity of the questions is going to go up a little bit. That would be kind of for your next exam. Okay, now next up, I want to talk about gel electrophoresis. I talked about DNA gel electrophoresis last time, and this is a technique where you can separate proteins based on their size. Now, the difference between, and you might hear this and be like, oh, separation based on size. Yeah, gel filtration chromatography. Not quite. Gel electrophoresis is different from gel filtration chromatography. What makes them different? One thing is when you do this gel, there's two major types of gels. There's something known as a denaturing gel and a non-denaturing gel. Okay. Now, I want you to think about that term, denaturing or non-denaturing. Denaturing is another way to put that is basically you've unfolded a protein. You've made it non-functional anymore. And in addition to that, in order to load a protein sample onto one of these gels, you heat it up to about 98 degrees. And not just because that's the old pop group, but because that helps to kind of unfold that protein. Now, when it comes to a denaturing gel, we use this substance right here, SDS, also known as sodium dodecyl sulfate. This is a detergent, sodium dodecyl, so 12 carbons, sulfate. So we've got a sodium and then this alkyl group that's 12 carbons long and a sulfate, SDS. Now, what this does is it provides a protein with a uniform negative charge. Now, thinking about that, oh, wait a minute, a protein with a uniform negative charge. Well, we've got amino acids that are your polar positive residues, polar uncharged, polar negative residues. Then we've got amino acids that are non-polar. This basically looks at a protein, and these blocks are going to be representative of individual amino acids. And we throw one of these molecules, SDS, SDS, SDS. We throw these molecules on each one of our each amino acid. So that means that we've got negative charges across the board on these amino acids. So that's how we get a protein. You know, think about a protein that's 600 amino acids. Well, now it's a protein with 600 negative charges because of 600 SDS molecules. Think about a protein that's 500 amino acids. Well, that's a protein with 500 negative charges because of these 500 SDS molecules. So we give these negative charges, and that means that when you run a protein, or sorry, when you separate proteins on an SDS gel, they all have a uniform negative charge. So that means that when you send this electric current through them, the charges, the net charges on these proteins are all, for all intents and purposes, the same. And they're the same because not in terms of magnitude, but positive, negative, or neutral. They're all negatively charged. So then you can separate them based on the magnitude of those charges. So if you think about if you've ever done DNA gel electrophoresis, you separate based on the same principle. The difference is a DNA molecule has an overall negative charge, which is different from proteins. Proteins can have charges that are, +7, +15, depending on the composition. Okay, so SDS is our substance that we use to basically give proteins uniform net negative charges. And that allows us to separate proteins and make determinations about their sizes based on how far they migrate. So anytime you run a protein gel, you'll have two columns, or at least two columns. One will be proteins, and these are all examples of example. Let me change that to example proteins with known sizes. Okay, so this is our way of comparison. So we'd have this mixture, and this specific mixture has myosin. It's got beta galactosidase. And these numbers right here are the number of Daltons that this protein is. So myosin is a 200,000 Dalton or a 200 kilodalton protein. Can anyone hear that in the background? Okay. Okay, a bit. Okay, it's not too disruptive. It's only disruptive when I say it's disruptive, somewhat disruptive. There we go. Okay. They're playing Astrobot and they're silly. These are my two kids, 7 and 5. And the other day, one of them said, "I wish we were twins." And I was like, that's adorable. You're not though. Okay. So anyway, we've got this mixture of proteins with known sizes. So this is a molecular weight, or MW, standards. So this mixture has proteins that we know the sizes of them. And then what we're able to do is say, okay, based on, we loaded it right here, how far did this protein migrate? How far did this protein migrate? How far did this one? And so on. So then we can say, okay, well, if a protein moves, let's say if it moves, I'm going to say 7.2 centimeters. If a protein migrates 7.2 centimeters, then let's say that this one right here is 7.2 centimeters. That protein is approximately 45 kilodaltons. Now, let's say that this protein right here, this next one, migrates, and that 7.2 centimeters is from the top, from its starting point, from its origin. We've got one that migrates 8.2 centimeters. That would be this next one. That's 31 kilodaltons. Okay. Now, based on their migration distance, we can say, okay, well, this one's approximately this size, this one's approximately this size. Now, then we can use that. Could everyone give me a 9 in the chat if they understand these molecular weight standards are for our comparison? Okay, great. We were going to compare those and basically use that as our data set so that when we have an experimental protein right here in or experimental sample in column 2, we can say, okay, well, we have a protein that migrated. Ooh, this one migrated. I'm going to say this one went approximately 7.8 centimeters. And we can say, okay, well, it migrated 7.8 centimeters. If it had migrated 7.2, we'd know that it's 45 kilodaltons. If it had migrated 8.2, it'd be approximately 31 kilodaltons. By virtue of this one migrating 7.8 centimeters, we can make an approximation and we would graph this, the relative migration versus the log of the molecular weight. We can say, okay, well, this one's approximately, I'm going to call it 36 kilodaltons. And these are just kind of rough off the cuff calculations. But this is a regression curve where we can plot, okay, migration distance or relative migration versus the log of the molecular weight. So that's the purpose of this technique of this. Now, that's using SDS page, which is our example of denaturing. Or it's a denaturing thing. Okay, now I'm going to give you guys a quiz, or not a quiz question. By the way, my computer might die before class ends. I hope I disappear. Hopefully I disappear. Okay, thank you for sharing. Okay, so here's the M1 question, the mid question. I'm going to go ahead and proceed from here. We talked previously about PI and isoelectric focusing as our separation technique. Now, I'm going to leave the question up. Okay. And, one of the things that's a challenge throughout all of this, can you show how the log thing? Yeah, sure. So basically, let's look at, I'm going to come back to this graph right here. Our x-axis is 0 to, it's a migration distance. It's 0 centimeters, 1 centimeter, 2 centimeters, 3 centimeters, and so on. Then on our y-axis here, you would take the log of the molecular weight. So you'd say, everything okay? Log of, let's say, 200,000. And when we plug that into the calculator, just a second. It's
What's this future sound?
it's okay. Log of 200,000 is 5.31 or 301. Okay. And then what I'm referencing is this particular band right there. And let's say, just for the sake of organization, I'll say that migrated 1 centimeter. So from here to here, that's 1 centimeter. Could you give me a 6 in the chat? Okay, cool. I'm following you. Okay. So I'm seeing some 6s, but I know what I'm getting at is I'm going to say this is after I've run all of the gel. I let it run for like an hour or something like that. And then I visualize it and I say, okay, well, here's where everything started. And then I say this is approximately 1 centimeter. Then I take that known protein size, and if you're like, how do we know that protein size? Well, that would be provided by the manufacturer of these molecular weight standards. They would tell you, hey, this molecular weight standards mixture consists of all of these proteins. It's got myosin. That's $200,000. So I'd say 200 log of 200,000 is 5.31. And so I'm going to plot that on my y-axis. So this is going to be my 5.31, and that corresponds to the migration distance, which we came up with is approximately 1 centimeter. Now, the next one is this band right here. And I'm going to say that one went 2.4 centimeters. Okay. Now I'm going to do the log of, what is that, 116,000? 116,250. Plug that in, and we get 5.06. So 5.06. Where did I? There we are. No, that's not good. 5.06. And so coming up with 2.4, 5.06, which is slightly higher. What am I doing? Oh, it's the negative log of that, I think. Yeah. So you'd plug those numbers in and come up with a curve that essentially looks like that. So then what you'd be able to do is say, okay, well, my unknown protein migrated this far. Here's my equation. Oops. Y equals mx plus b. Plug in my x value, and I'd be able to solve for my y, take the anti-log of that, and there you go. There's the molecular weight. A rough approximation of the molecular weight. Okay, so this is a valuable technique because it does give you a way of saying, okay, well, I expected to purify a protein that's